All right, so this is where we've been. You should already know how to do this. So for this chapter 4 is so huge, I want you to see how it all ties together. So we started off just finding antiderivatives of a basic function, and then when they weren't so basic, we used some u substitution. But that was just what's the antiderivative of x squared with respect to x? And you guys would tell me it's x cubed over 3 plus c, and you'd move on to the next one. And then after that, when they got a little ugly, we did some u sub, but this was pure mechanics. You didn't really know why you were doing this, you just knew the process. Then what we did is we started talking about area under a curve. And we first started approximating it. So we said you have this funky curve that you can't get the area under, but we chopped it into rectangles that hit on the left or rectangles that hit on the right or in the middle. Then we did some trapezoids, and it was doable, but it was an approximate because sometimes our rectangles were over and sometimes they were under. So we were getting decent approximations, but they weren't great. Then we started talking about the definite integral. Remember the difference for a definite integral down here is if you put these limits on it, and what that tells you is to get the exact area under the curve, like on this one from 1 to 4. And we said we started doing them exactly, but they had to make very specific geometric shapes like triangles and circles. Otherwise, we couldn't get it exact, but we were able to do it if they were super nice. So now what we're going to start with today, it's going to be back to mechanics again, because we are going to take the mechanics that you learned in 1 and something called the fundamental theorem of calculus to be able to figure out the exact area under the curve when it is going like this. So it's no longer approximate, and it doesn't make a geometric shape. I have no clue. There's no formula in the world that can give me the area of that shape, but I can find it with calculus, not with a formula. And that's called the fundamental theorem of calculus. So that's what we're going to do today. Then after that, we're going to start applying this stuff to actual word problems, like where you're actually applying it to a lot of physics, actually. So in your notes, we're going to do the fundamental theorem of calculus, and it's nice and easy. We'll write that in tomorrow. So we'll be right here. I'm going to show you what it says, then I'll demonstrate it. The proof for this is actually in your book, but it's too difficult for you to understand right now. So I wouldn't, just kind of like when you first learned Pythagorean theorem, nobody ever told you why a squared plus b squared was c squared, you just did it. That's going to have to be what this is for a while, because you won't understand the proof of it yet. Anyway, what it says, the fundamental theorem of calculus says this. In notation, it says the definite integral, which means the exact area under the curve, as long as it's continuous, which makes sense, can be found. So now we're going to be getting the exact area under the curve, and we can find it with a formula, actually. So you got to remember what capital F stands for from 4.1. That means the antiderivative. I'm going to review that just to make sure you remember what that is. What's the antiderivative of x to the 4th? Go ahead and tell me. I know I have this thing on. X to the 5th over 5. Yeah. What's the antiderivative of cosine x? Sine x, exactly. So you're going to be fine. Those are what the big F of is. So really you're going to be able to do it by just finding antiderivatives and plugging numbers into them. That's what this means. Antiderivative at B minus antiderivative at A. So we're not going to use geometry. We're going to use what's called analytically or algebraically. We will get the exact area under very strangely shaped curves without even needing to graph. Here's the process. It's really easy to use. So today's is kind of the basics, the easiness of it. Here's my function. I am going to find the area under the curve from -1 to 2 of this function. This function is curvy, so I couldn't do this with geometry. How do I know it's curvy? That's a good question. Yeah, it's because it's a parabola. So we don't have a formula for that, but what the fundamental theorem of calculus says is to do this. It first says to find the antiderivative. And in the formula, that's called big F of x, but that's just notation. You just need to know how to find an antiderivative first, which we've already done, and you guys were really good at it. So let's go take a look. What is the antiderivative of x squared? x to the third over 3. So this is what this says, that what you're going to do is take x squared minus 1 dx, and you are going to, because it says it equals, the antiderivative. So I'm going to give you some notation here. The antiderivative is x cubed over 3. We add 1 and divide by that. Minus, what's the antiderivative of 1? X, yeah. And technically, what else is there? Carl. I'm not going to put him on there, and we're going to answer the question of why there's no Carl in a little bit. There's a reason why you don't need to put him on. You could, but he self-destructs. So we are going to do the antiderivative, and the notation for that is then to write a bracket, or usually it's a straight line, but I like to bracket it off and go from -1 to 2. So the first thing you're going to do is get out of that integral by doing an antiderivative, and you're going to put your limits over on the right. The next thing you do is you plug the top limit in. That's what this is right here. Antiderivative at b. B is the top limit. So you take b and you dump it in. Just arithmetic. So you're going to say 2 cubed, which is 8, over 3, minus 2. All I did, notation-wise, that's this right here. The antiderivative with a b plugged in. That's what that says. Then according to this model right here, what does it say I'm supposed to do next? According to the model, what am I supposed to do? Subtract. So then subtract. So let's go minus the bottom plugged in. That's poor grammar, but you get what I'm saying. The bottom plugged in. And then here's what I'd also suggest. It's a detail that'll save you from making a zillion sign errors. Put that in parentheses. So we do the antiderivative with the top plugged in, and then we do the antiderivative with the bottom plugged in. So next I'm going to plug in a -1. Make sure you put parentheses or even beefy brackets if you want to keep it sorted out. But now I'm just going to put the bottom limit in and do a little arithmetic. -1 cubed is -1. And then I'm going to have minus a -1. So plus 1. There's a huge opportunity in these for sign errors, so be pretty methodical. Next thing you do is the arithmetic. So there's going to be lots of fractions and lots of signs. I'm going to give you a little way to combat that without making mistakes. Don't go to your calculator because you wouldn't have one. When you can use one, go ahead, but you normally won't have one for one like this. What I would suggest you do is take care of this first, either in your head or if it's ugly, get a common denominator, but everybody should be able to tackle -1/3 plus 1 without an issue, right? What do I got? 2/3, okay? So I'm going to be subtracting 2/3. And then if you have ugly fractions, get a common denominator, but these aren't very ugly. But if they were, let's just go ahead. I would change that 2 to 6/3, just so everything has a common denominator. Now subtract them, and what do you get? I get what? 0. I want to show you the graphical tie-ins because now you're going to be not looking at graphs, so I think you're going to lose what you're doing. However, do you think your calculator does these? Yes, those of you with a graphing calculator, take it out because you can check on your calculator, and later when they start being physics problems and the functions, because in physics things don't move this nicely. They're usually got funky paths, and you'll have to use your calculator, so I want to make sure you know how to do that. So take out your calculator. Do you remember what command it is on your graphing calculator? Yeah, Math 9. In case you didn't bring your calculator, make sure you try a few at some point, because at the end of the week, it's all going to be on the calculator. Today, we aren't going to use it, but I want you to know how to check it. So you're going to go to Math 9, and your calculator will do this exactly. You just need to enter the bottom in when it asks for it, and then the top in when it asks for it. Enter the function in question, it'll ask you, and then derivative with respect to x. Hit equals, and your calculator has been programmed to basically sum up an infinite amount of rectangles until it collapses in on an answer. And what does your calculator say? It should. If you entered it right, it should say 0. You don't need to put this in your notes, but I want you to understand what this means when it says the area under the curve is 0. It doesn't mean there's no area under there. What does it mean about the curve, probably? Yeah, Exactly. There's the same amount above the x-axis as below the x-axis. And you don't need to draw this, but I'm going to show you graphically because that's actually more important that you understand what you just found. X squared minus 1 is a parabola. It opens down, right? At -1, it's at 0. At 0, it's at -1. At 1, it's back to 0. And then at 2, it'd be at 2 squared minus 1. It'd be up at 3, like up here. So it's going like this. So the answer 0 is, you got this part, right? And when your calculator integrated from there to there, what did it get? Not a number, but it got negative, right? And from here to here, this is positive. And what it means that you got 0 is those are actually completely balanced out. Does that make sense? So the next question of why is there no C? Where in this process do you think Carl completely just disappeared? Something, the subtraction, exactly. I could have put him in. He would have been right here as plus C and right here as plus C, but he would have been plus C and then a minus C, and he would have disappeared. So the reason Carl's not there is no matter what the constant was, it would have canceled. So let's write that cancels in the subtraction process. So with a definite integral, you do not have a plus Carl, because once you subtract those two, he's gone. All right, so we're going to do 3 of them, and then you're going to go do homework for a little bit, and then we'll come back. This was for people who are absent in case I didn't video, so you can go ahead and go right to here. We'll just do 3, and then I'm going to have you work for about 15 minutes. Just wait on that. All right, so we're going to evaluate each, not on our calculator, but by hand. Let's go take a look at the process. The first thing you need is the antiderivative, which, yeah, go all the way to here. It'll be a few pages in. The antiderivative of x squared would be x cubed over 3. The antiderivative of 3 is 3x. No need for Carl because he'll disappear. The notation is we write it like this. You'll see it with a straight bar. I like to put a little bracket on it. I just like it better, but it doesn't matter. Anyway, and you put your limits on the outside. Then what do? Put the 2 in, yeah. Kind of think of the top falling in there first so you don't accidentally put the bottom limit in, but 2 is going to get dumped in first, and we're going to go 2 cubed is 8 minus 6. There's the top one plugged in. Then do you remember what? You probably have the process down already because you guys are smart, but what next? Top in and then what? Yeah, you're going to subtract off, put brackets or parentheses or something so you don't make a sign error. Then you put the bottom in. So when you put in a 1, you're going to get a 1/3 minus 3. You'll have to be able to crank this out. Arithmetic is really to your benefit. So if you're not comfortable with fractions and signs in arithmetic, this becomes kind of an issue. So the best thing to do if you're not comfortable is go all common denominator. Again, if you don't need to, don't. But take 6 and write it as 18/3. Take 1/3 and leave it. Write minus 3 as 9/3. Again, if you're good with your arithmetic and you can crank that off without a calculator quickly and you're accurate, do it. But if you make mistakes, go all common denominator once you get it laid out, because then it's pretty easy. Then I would take care of your beefy brackets, and that's going to become a what? Minus 8/3, correct? So when I'm all done with this, I've got 8/3 minus 18/3 for a negative 10/3. Then I've got minus a minus, so I'll have a plus 8/3. The answer to this is negative 2/3. What does that mean about the curve itself? What did it end up having? Yes, more quantity or more area below the x-axis than above. I'm not going to go graph it, but that's what that means. So the next one up, what do you think I'm going to suggest you do with the constant multiple? Bring it out front. It does always make things easier. So we're going to make that just a quick rewrite. We're going to go 3 times the integral from 1 to 4 root x dx. There won't be any u substitution today. That actually comes later. So these will be nice just so you get the process down. Easy ones to derive. All right. So then I'm going to take that 3 because it can just hang out front. I need to do the antiderivative of x to the 1/2. Do you guys remember what that is? Yes, add 1 to it, so get x to the 3/2. And then divided by 3/2 is 2/3. So just be really good with your fractions. And I'm going to be evaluating that from 1 up to 4. These can cancel because you have the 3 on the top and the 3 on the bottom. So I'm going to do a little rewrite. I've got 2 left. I've got x to the 3/2 left, and I'm going from 1 to 4. And then this is where you can make a decision. If you want to take the 2 with it, you can do 4 to the 3/2 minus 2, blah, 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 or you can factor the 2 out right away and then leave it out front. What do you think is safer, leaving it out front or putting it in? It's safer to leave it out front, especially when it gets ugly. Like if it's a -1/5, you don't want to be putting that in and then subtracting it. There's more room for error. So even though this 2 is easy to work with, I would just get in the habit of pulling that out front and then doing the rest of it. So again, top 1 in first. So I'm going to do 4 to the 3/2 minus 1 to the 3/2. And there's a lot of manipulation, and the speed that you guys do your homework is going to be very different. It depends on how fast your arithmetic is, depends on how well you work with fractions, depends on how well you know your fractional exponents. What is 4 to the 3/2 without a calculator? Because you won't have one. That's a I would love to let you use one, but you won't have one even on the AP exam for one like this. Yeah, it is 8. So how do you get that 8 quickly so that you're not you have 2 options. You can do 4 cubed, which is 64, right? And this is the root. So square root. Or you could do this. You could do the square root of 4 and then cube it. That's what I would suggest, because then you're not working like if this had been a 5 on here, you don't want to do 4 to the 5th in your head. You know what I mean? But the square root of 2 to the 5th is easy. So I would do this, the root first. Square root of 4 is 2. And then cube it and get your 8. So you're going to get 2 times 8 minus 1 to any power is 1, so that's nice. What that means is my answer is 14. Let me show you graphically what you just found. You don't have to make a graph, but let's go plot that on there. See if you remember, what does the square root function look like, just in general? Yeah, it does exactly that. It does that shout out function like this, right? The 3 in front of it right here just stretches it higher. So at 0, 3 root 0 is still 0. At 1, you'd be up at 3 instead of 1, 1. And like at 4, you'd be up high. It's just going to go like this higher. What does that 14 represent that we got? Yeah, the collected area under the curve from 1 out to, far did we go? 4. It's giving you this, which is, what would be a good shape that would approximate that? What would be a really good, a trapezoid would have been a good approximation, but it wouldn't have been exact because of this curvature right here. This is exactly what it is. All right, last one up, we'll do a trig, and then you're going to go work on your homework until the last 10 minutes. Where I need to discuss absolute value. So same thing with the trig. If they're giving you a trig one, you should know the antiderivative, or you should be able to play with it and find it. What is the antiderivative of secant squared? Tangent. Yeah, the derivative of tangent is secant squared, so let's go do that. It's from 0 to pi fourths. And then I'm going to pause for a second. If it's not in your face like this one is, it means it would be if you did something, because there won't be something you don't know. So what you might see is something like this in your homework. I'll just put a fake one on here. Maybe this is sine squared on the bottom. Maybe you're integrating, I don't know, from pi over 2 to pi over whatever. It doesn't matter. But this is not in your face. But if you do one small thing, it will be. What do you think? Splitting apart is always a good option. But on this one, there's even a better one. Yeah, the top. What is 1 minus cosine squared? Sine squared, right? So that's actually sine squared x over sine squared x if you just played with a little bit, which is 1. And what's the antiderivative of 1? X. So if it's a trig one and it's not in your face, you need to do a tiny little play. It won't even be a lot. It'll be something very basic. So let's go do this one. We put our top boundary in first. We get tan pi fourths minus tangent 0. So again, although the fundamental theorem of calculus is really isn't this kind of easy, right? Where do you think the danger lies? all the algebra, the arithmetic, the trig, the sign errors, that's the issue. The actual calculus is the easiest part of all of this because it is easy. But then people will forget this or forget what that is and it goes south, or they forget a minus somewhere or their fractions. So you just got to be really careful. 100% sure, what is tangent of pi over 4? 1. Why? It's sine over cosine, and at pi over 4, they're what? I don't even care what they are. I care that they are equal, right? So this is 100% sure 1. Tangent 0 is sine 0 over cosine 0. Sine 0 is the y value, cosine's the x. So 100% sure what's tan 0? 0, but they won't all be that easy. Like they'll always be on the unit circle, but there might be like a 2 pi over 3 or a 7 pi over 6 or something. So you really have to be good at your unit circle without looking it up. So you have to just be careful with that. Go to your calendar. That's on the front page. And I'm going to have you open up. I'm going to tell you what I want you to do with it. On the very front page, you have a calendar. And this week, right here, you're going to have one big thing that comes in. And the first part of it is bookwork, and that's for today and tomorrow. So across this whole thing is where I want you to write the book assignment. When's everything going to be due? Actually, Tuesday. We don't have school Monday, so go cross that off. You will have a bookwork assignment, and then there's a packet that has 3 worksheets for these 3 in it. But I'm going to collect it all in one chunk. Yep. It's President's Day. It's Martin Luther King Day. Sorry. That doesn't. Whoops. You're wrong day. All right. Anyway, under there, I'll have you put the assignment. It is. Sorry about that. Wrong day. That's what you can stretch out across the bottom there. This assignment, we're going to work right now until the first person gets to number 21 or it gets to be 5-2, one or the other. I need about 10 more minutes to talk about absolute value, but the first one with absolute value in it is number 23. I just want you to practice a little bit without that. So again, stretch this assignment all the way across the bottom. You can't get past here today. These will come into play tomorrow, but just write the whole thing down. You should be good to go. So open up your books to page 293 and work for about 20 minutes or until the fastest person, I don't want anybody waiting, till somebody hits 23, and then we'll stop. So I'm going to pause the video till we go back. So go back to your notes, and then we'll tackle the absolute value that's on this page. You should have a similar graph. I had to move this over. My mic was dying. All right, so there is no antiderivative for absolute value. Your calculator, though, will still do it. So those of you with a graphing calculator, it'll tackle absolute value, no worries. So let's go get the answer before you start. Go to Math 9. It'll pop up your integration symbol. Go from 0 to 2. And then to get the absolute value bars, that's math. So hit math again. And use the right arrow over to num, and it'll be the first option. So as you're working your graphing calculator, Math 9 to get the integral symbol up. To get the absolute value on your calculator, hit the math again, head over to num. I think it's the first option, isn't it? Yeah, and it'll pop the bars up for you. Go ahead and enter 2x minus 1 with respect to x and hit enter. And on your graphing calculator, it'll give you the answer. I think it's 5/2. 2.5, 5/2, depending on whether you're in decimal or fraction mode, but we know that's what we need to get. The problem is, how do you do that if you don't have a calculator? Because if I were to ask you, what's the antiderivative of absolute value, you don't know, and it's not because I haven't told you, it's because I can't. There is no function whose derivative is the absolute value. So here's what you need to do. You have to go back to the formal definition of absolute value. In elementary school, they tell you, oh, it's always positive. It's that, which is true, and that allows you to do the absolute value of -3 and make it 3, right? And then in middle school, they say, well, it's always positive because it's a distance from 0, and that helps you and you use it then. But at higher levels of math, you have to have a formal definition so you can combat how to take absolute value and rewrite it. And really, absolute value is a piecewise function. It's a line that goes up in one direction and down in the opposite direction. So it's two lines pieced together, and it's really itself. Like the absolute value of 7 is 7. It's itself as long as you put positives in there. Whoops. So if you put any positive number into the absolute value function, you might as well not have done absolute value, right? Absolute value of 3 is 3. But if x is less than 0, how do you mathematically tell me what its absolute value? Yeah, it's the opposite. So the absolute value of -5 is the opposite of -5, which makes it positive. So formally defined, the absolute value function is pieced together with two lines. And where you split up your lines is where this vertex is, right? And to figure out where the vertex is, you need to know where it's 0. So the first thing you have to do is go to your chunk inside of the absolute value, and you have to figure out what makes that 0, because you need to find the vertex. So what makes 2x minus 1 equal to 0? A half, and that's why this has a vertex right here at a half on my graph. So at x greater than or equal to a half, I'm going to split it into one line, and at x less than a half, I'm going to split it into another line. So as long as x stays bigger than a half, like 5 or 10 or 100, I don't need the absolute value bars because it'll be positive. If I put a 10 in there, I'm at 20 minus 1 is 19. I don't need absolute value. So to the right of x equals 1.5, this is the line that's exactly what it doesn't, I don't need the absolute value bars. But to the left, I have to take the opposite of it. So when I take the opposite of 2x minus 1, I get a negative 2x plus 1. That's what this line is negative 2x plus 1. So the way you can get around absolute value in integration is to take it and do it from here to the vertex and then from the vertex to the right. So you split it into two integrals. So when I integrate, let's go write that down. We're integrating from 0 to 2 absolute value 2x minus 1 dx, which our calculators already told us was 5/2. How do I combat it? And this is going to come in our physics problems because we're going to be finding total distance something travels, and there's going to be absolute value in the formula, and you're going to have to figure out how to get around that. And here's how. You find out where this is 0. Where did we say that was? At a half, and you're going to integrate from the lower limit to 1/2, and that will be, excuse me, this function, right? The negative 2x plus 1 dx. Then you're going to go along this line right here for the rest of the integral, which is from 0 to 2. And for that one, I just have the same function. So I'm going to repeat what you do for absolute value. You have to find where the dividing spot is between positives and negatives. To do that, you find 0. That's the vertex. To the left of that, we do the negative or the opposite of it. That's this one. To the right, we do it itself. And then you can just integrate it as we've been doing the other ones. What's the antiderivative of negative 2x? Over 2, which is what? Negative x squared. So that's going to be a negative x squared. Take its derivative, you get negative 2x. That checks out. Plus, what's the antiderivative of 1? X, perfect. I'm going to do that from 0 to 1/2. And that'll give me, by the way, I didn't need calculus for this one. Why not? Technically, I could have done this with 8th grade, 7th grade math, trying exactly. This one actually does make geometry, so I could have just aborted all calculus right here, but I'm not going to. So then I'm going to go from 0 to 2, and so that would be x squared. It'd be 2x squared over 2 minus x from 0 to 2. If this checks out, I should get 5/2. So let's go do that. And again, watch your signs. What is negative x squared when x is a half? What do you think? What do you think the danger is of that? It is negative 1/4. What do you think a lot of people put? They do. They put a fourth because they think, oh, I was taught that a negative times a negative is a positive. That's super true. But this negative is out front, not in it. So this is actually a negative, or the opposite of 1/2 squared, which would be 1/4. And then plus a half when I put it in, and then it'd be minus 0 plus 0. So I'm not going to put that in. I'm not going to put the lower boundary in. So what I get when I do negative 1/4 plus a half is 1/4. That's the area of this triangle right here, which looks good because it's a half of its base, which is a half, times its height, which is 1. So that's what this is. Then I'm going to go over and do this bigger chunk right here, and I'm going to do it analytically, not on the graph. So I'm going to put in a 2, and I'll get a 4. Right? Minus 2. I might as well write that down. So 4 minus 2. Then what? How far did, oh, yeah, that was a half down there. You can't see it very well. Then I need to plug in a half, but don't forget you're doing a minus. So you're going to have minus 1/4 minus a half. And if you do the arithmetic, you are going to get 2.5 or 5/2. I'm not going to finish the arithmetic on it. So the moral of the story is go look at number 25, because that, or is it 23 that has absolute values in it? 23? 23. Let me just take a peek. What's in the absolute values? 2x minus 5. Where is that equal to 0? 5/2. So you're going to have to integrate up to 5/2. I don't even know what the lower limit was. Can you tell me? What was the 0 to 5? So you're going to have to go from 0 to 5/2 first. And in there, you can use what? The function itself or the opposite of the function? If you don't know, put in a 1, which is in here, and you're going to go negative. You need the opposite of it. So you can just self-correct it. So that'd be negative 2x plus 5 dx. But for the rest of the integral, from 5/2 up to 5, you can do it as it stands. If you put in like a 3 in here, you're going to just get 1. You don't need absolute value bars. So you can just do 2x minus 5. So that's how you combat absolute value. It's not due till Tuesday the